If you were given this integral, you might take a look at it and think, this is not possible. Well, you'd probably be right to think that. But it is possible if you know this trick. And it's not really a trick, it's more just something you do. If you can convert from xy coordinates, aka Cartesian coordinates, to polar coordinates, this integral does in fact become possible. So how do we do that? Notice that there's a lot of things we have to change about our integral. First of all, we need to know that our r and our theta mean different things than our x and y. R implies what you think it means. It means radius. And our theta implies exactly what you think it means as well. It means our angle. So the first step for most multiple integral problems in multivariable calculus is to draw the region of integration. Let's take what our x is bounded by. Our x is going to be bounded by our 0 and our square root of 9 minus y squared. So let's just write this inequality right here. Right? Now, let's take into consideration this part of the inequality right here, right? Let's just write it out. X is going to be less than square root of 9 minus y squared, right? Squaring both sides gives you x squared is less than 9 minus y squared. Take the y squared to the other side, you get x squared plus y squared less than 9. What does this look like? Well, if you said circle, you're right to say it looks like a circle. So we know that we're integrating over a circle of radius 3. So let's draw the shape of this circle. So we said that this circle is a circle of radius 3, right? So just at the boundary right here, I'm just going to write a little 3 to remind us that the radius of the circle is 3, right? Let's take into consideration the other part of our inequality. 0 less than or equal to x, right? Which you can also write as x greater than or equal to 0, right? This should tell you that we are only going to consider the right half of our circle because the values on this side are in the negative x and the values on this side are in the positive x. So automatically we know that we are working with this side of the circle, right? Now there's one more thing we have to consider. Now let's write our inequality for y. It'll tell us the last part of what we need to finish getting the bounds for this interval. 0 is less than, y is less than or equal to 3, right? Now, what does this tell us? This tells us that we are only going to be considering the positive part of y. So it actually means that this part right here, which is the negative y, we're not going to be concerned with. We are going to be concerned with this part, which consists of the positive y. So finally, we can kind of fully draw this region of integration. We're only going to integrate this small slice of our circle, right? Because we're only concerned with the positive values of y and the positive values of x. What region or quadrant only has the positive values of x and y? It's the region that I shaded in red, right? And now we can try and figure out our values of r and theta to get our bounds. So let's start with r. R is simple. We already said that our radius is from 0 to 3, so we know that our r bounds are going to be 0 to 3. Our theta is a little bit more tricky, but if you know how the unit circle works, it's not actually that tricky. Let's just think of the unit circle. The unit circle goes from 0 to 2 pi, right? In our case, we're starting at 0, right? We're going to trace from 0, keep going, and we're stopping right here. If you think of the unit circle, what value is this right here? It is simply just pi over 2, right? So we know that our theta bounds are going to be 0 to pi over 2. And now we're done, right? We can kind of fully set up this integral. So let's draw a little bit of an arrow down here now that we know our bounds. And let's just write the double integral first of all, no bounds yet. So now that we found our bounds, we can kind of start replacing things inside of our integral, right? This square root of x squared plus y squared has to become something in terms of r, right? Well, what we can do is we can recall that x equal r cosine and y equal r sine of theta, right? So now we can kind of write this in our integral, right? Let's just do square root of r cosine squared, right, plus r sine theta squared. Write another line down here. We're going to get r squared cosine squared theta plus r squared sine squared theta. One more step. We can factor out an r squared from both of these, right? And now what does this become? This just becomes simply 1, right? So we're going to write another part over here. It just becomes the square root of r squared times 1, right? And this is just simply square root of r squared. And then the square root of r squared is just r. Look at that. So our entire part of our integral just becomes r. And now an important rule of polar is that your dx dy is always going to become, or it could be dy dx, right? R d theta. So we can write this down here. R d theta. What does this tell us? It tells us that we're integrating with respect to r first. We know our r bounds are from 0 to 3, right? So we can write 0 to 3. And then our theta bounds are from 0 to pi over 2. And now we can simplify the inner part of our integral a little bit, where it becomes r squared dr d theta. And now this menacing integral up here, x squared plus y squared, the square root of that, who wants to integrate that, has become simply a power rule, inverse power rule, right? So how would we do it? Well, keeping the 0 to pi over 2, because we don't care about it yet, we're not dealing with it yet. We're just going to have our r cubed over 3, because inverse power rule, from 0 to 3 d theta, and then keep parentheses for good measure, right? How do we evaluate it? We can just do the fundamental theorem of calculus inside of our integral, right? We're going to be dealing with 3 cubed over 3 minus 0 cubed over 3. That's just going to become 0, right? And then 3 cubed over 3 is just 9. So we're really finally left with 0 to pi over 2 of 9 d theta, right? Now, one final step, what we can do is we can integrate the theta, d theta, right? The integral of d theta is simply just theta, so you're going to have 9 multiplied by theta evaluated from 0 to pi over 2. And then what you can do is you can evaluate that using FTC as well. And then your final answer is just 9 pi over 2. That's it. So this scary looking integral becomes something that you can integrate very, very easily by simply converting to polar coordinates. And all of the work becomes 9 pi over 2. That's how you solve this problem.